A team spent 2 full days hunting a cascading failure in their Kubernetes cluster, only for an AI model to find the root cause after ingesting 5 days of logs in seconds. This isn't just faster search or a chatbot trick. It marks the moment AI inference moved from being a conversational novelty to becoming an autonomous system diagnostician. The capability relies on specific hardware architectures that allow processing terabytes of sequential text without traditional indexing, fundamentally shifting how engineers handle unstructured data. For years, developers have treated log files as structured data to be indexed and queried with keywords. When a complex failure occurs across multiple services, the signal gets lost in noise, requiring manual correlation over days. The breakthrough here is not just software efficiency, it is a hardware-enabled paradigm shift known as Generative Information Retrieval. This approach leverages high-bandwidth memory and massive parallelism to process unstructured text directly within a model's context window. Instead of searching for patterns that match specific strings, the system synthesizes complex log sequences to understand the narrative of the failure. This capability is enabled by modern GPU architectures designed for inference at scale. Research from UIUC and Cornell University demonstrates that these systems can handle semantic reasoning on massive logs without traditional indexing frameworks. By utilizing unsupervised clustering and multi-round attention mechanisms, a new framework called LLMID reconstructed fault chains with a 16.2% improvement in accuracy compared to current mainstream methods. This statistical gain is not theoretical. It translates directly into the ability of an AI agent to distinguish between noise and critical failure signals that human engineers might miss after hours of fatigue. The hardware reality behind this shift is often overlooked by software teams who focus solely on code logic. Data from the Delta supercomputer reveals a stark contrast in component reliability within these systems. GPU memory has been shown to be over 30 times more reliable than other components, such as the graphics system processor found in newer architectures. However, even with this resilience, single-component faults like GSP errors can still cascade into node drains lasting up to 23 hours. This underscores why inference must happen at scale. Detecting these cascading failures requires processing massive telemetry streams in real time, a task only feasible with the current density of high-bandwidth memory and parallel compute capabilities available on modern accelerators. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. We are moving from searching structured data via keywords to an era where AI acts as a system diagnostician by synthesizing terabytes of unstructured text directly within the context window. This shift changes the engineering workflow entirely. Where teams once built custom indexing pipelines for every log type, they must now design systems where massive context windows are treated as primary data sources. The ability to run this system diagnostician model depends entirely on the memory architecture of the chip running it. Engineers who ignore these hardware constraints will find their inference engines bottlenecked by latency, rendering them useless in real-time crisis scenarios. The human factor adds another layer of complexity to why this shift is necessary now. A longitudinal study involving 800 developers confirms that while AI coding assistants increase code output, they also shift developer behavior toward higher context switching. The 2 days spent on a problem mentioned earlier represents an inefficiency that hardware-enabled inference can eliminate. When engineers are forced to manually triage thousands of log lines, their cognitive load increases significantly, leading to errors and slower resolution times. By offloading the synthesis of these logs to models capable of understanding context natively, teams reduce mean time to resolution from days to seconds, allowing developers to focus on architectural fixes rather than signal hunting. This evolution signals a fundamental change in tooling strategy for software engineers. The era of building custom indexing pipelines is ending as we move toward treating logs as narrative text for models to read. This requires practitioners to evaluate hardware choices not just for training speed, but for inference latency in diagnostic scenarios. The choice between compute density and memory bandwidth becomes the critical decision point when designing systems that must handle real-time failure analysis. Teams that fail to adapt their infrastructure to support these massive context windows will find themselves unable to leverage the full potential of modern AI capabilities. The statistics backing this transition are clear. New frameworks utilizing high bandwidth memory have demonstrated a 16.2% improvement in fault location accuracy compared to traditional indexing methods. This is not a marginal gain. It represents a qualitative leap in how systems can be monitored and maintained. Furthermore, the odds of foregoing manual intervention when such tools are available rise significantly, as teams realize that human triage simply cannot compete with the throughput of an AI system trained on massive context windows. The data suggests that over 40% of developers now treat these predictive authorities as essential to their workflow rather than optional novelties. The implication for your career and your stack is immediate. You are no longer just writing code or debugging scripts. You are designing systems where the AI itself becomes a first-class component in the observability pipeline. The ability to feed terabytes of context into an inference engine without breaking memory constraints defines the next generation of reliable software infrastructure. As these models become more capable, the barrier to entry for complex system diagnosis lowers, but the requirement for robust hardware support increases. The future of engineering is not about replacing human intuition with automation. It is about augmenting that intuition with a tool that can see patterns across terabytes of data instantly. The question now shifts from whether AI can help debug your systems to whether your current infrastructure is ready to feed these models the massive context they require. If you are still relying on keyword search and manual log correlation, you are operating at a significant disadvantage in an environment where seconds matter more than ever before. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.